Hey. So I need to tell you something about black holes that genuinely unsettled me when I read it. And I think by the end of this video, it's going to change the way you think about, well, honestly, the way you think about everything above your head. We're going to cover a lot of ground. I'm going to take you through 8 discoveries, each one of which, on its own, broke something scientists thought they understood about black holes. And by the time we reach the last one, the picture you have of what a black hole actually is will look nothing like what you started with. If you're still here at the end, do me a favor. Hit subscribe, because this channel exists to find the facts that change how you see everything. And this one changes a lot. Let's start with the thing that came out 2 weeks ago. On July 28, 2026, a team at Tohoku University in Japan published a paper in Nature Astronomy. And the finding was simple to state, but very hard to sit with. Black hole winds are 100 times more powerful than anyone thought. Not a little stronger. Not, we revised the estimate upward 100 times. That is a factor of 100 applied to something we thought we already understood. Here is what that means in physical terms. When a supermassive black hole feeds, when matter falls toward it and heats up, it does not just pull things in, it pushes things out. Gas, radiation, energy, blasting outward in what astronomers call feedback winds. We knew those winds existed. What we did not know was how far they reach. The team measured the turbulence caused by these winds in a galaxy cluster, and they found that the energy carried by the wind extended roughly 300,000 light years from the black hole. 300,000 light years? The Milky Way itself is about 100,000 light years across. So these winds reach 3 times further than the entire diameter of our galaxy. A single black hole, sitting at the center of a distant galaxy, is shaping the gas and the conditions of space far beyond the edges of its own home. That is not a local phenomenon. That is a black hole reaching out and touching the universe around it on a scale that, honestly, sounds wrong when you first hear it. The lead researcher, Satoshi Yamada, put it plainly. Black holes are largely known for sucking matter in, but they also eject gas in the form of powerful winds. And those winds, it turns out, are not a side effect. They are a force that reshapes the space between galaxies. Now, here is why this matters beyond just the number. For decades, astrophysicists have been trying to solve a puzzle. Galaxy clusters, the largest structures in the universe, contain enormous amounts of hot gas. That gas should be cooling down. When gas cools, it collapses. When it collapses, it forms stars. So galaxy clusters should be producing stars at an enormous rate. They are not. Something is keeping that gas hot. Something is pumping energy into it, preventing it from cooling, preventing it from forming stars. And the leading candidate for that something has always been the central black hole, its jets, its winds, its feedback. But the old estimates said the winds were too weak and too local. They could heat the gas nearby, but not across the whole cluster. There was a gap in the energy budget. The black hole was not powerful enough to do the job. This paper closes that gap. 100 times more powerful means the wind can reach the gas at the edges of the cluster. It means the central black hole is not just influencing its own galaxy, it is regulating the temperature of the entire neighborhood. One object, millions of times the mass of our sun, controlling whether stars form across a volume of space hundreds of thousands of light years wide. And that is just the first thing we got wrong about black holes. The second thing that changed recently is even stranger, because we always assumed we knew where supermassive black holes live. The answer was simple: the center. Every large galaxy has one, sitting at the very middle, anchored by gravity, surrounded by the densest concentration of stars. That was the rule. For decades, nobody had a reason to question it. Then on August 5th, 2026, 11 days ago, a team at the University of Maryland published something that broke that assumption. They found a supermassive black hole, Enum 30,000 light-years from the center of its galaxy. Not a small black hole, not a stellar mass remnant drifting through space. A supermassive one, millions of times the mass of our Sun, sitting roughly a third of the way out from the core. And here is the part that makes it genuinely disturbing. It was invisible, completely invisible. It was not feeding, it was not producing jets, it was not emitting X-rays or radio signals or anything at all. It was just sitting there, in the dark, doing nothing, undetectable, until a star wandered too close. The black hole ripped it apart. The process is called a tidal disruption event. The gravity gradient across the star exceeds the star's own binding energy, and it gets shredded into a stream of superheated gas that briefly lights up across the electromagnetic spectrum. For a few weeks, the black hole became visible. A flare of light, picked up by a survey telescope scanning the sky. And when astronomers traced it back, when they calculated where the flare came from, they found something that did not fit the model. The flare was not at the center of any galaxy. It was off to the side, way off, 30,000 light-years off. The lead author, Gezari, said it plainly. Until now, we have started with the assumption that supermassive black holes reside in the centers of massive galaxies. This discovery will have a huge impact. So how does a supermassive black hole end up 30,000 light-years from where it should be? The most likely answer is a galaxy merger. Two galaxies collided at some point in the past. Each had its own central black hole. When the galaxies merged, the black holes did not immediately find each other. One of them, the one we just found, got displaced, knocked sideways by the gravitational chaos of the merger. And it has been drifting ever since, a wandering supermassive black hole. Think about what that implies. If this one exists, there are probably others, lots of others, drifting through galaxies, including ours, completely invisible, completely undetectable, until something wanders close enough to die. Gezari's team estimates that as new survey telescopes come online, particularly the Vera Rubin Observatory, we could go from finding a few of these per decade to finding hundreds, maybe thousands. The universe may be full of invisible supermassive black holes, scattered through galaxies by ancient collisions, sitting in silence, waiting. And we had no idea. Now, if you have been following this channel, and if you have, thank you seriously. You might remember one of our earlier videos. It was called Black Holes Are Being Built Out of Other Black Holes. And it did better than almost anything else we have posted. The reason, I think, is that the idea is genuinely hard to sit with. We think of black holes as endpoints, the final stage. A star lives, it dies, it collapses, and that is it. Done. Except it is not done. Because some of them collide with each other. And when they do, they produce a bigger black hole, one that is heavier than either parent. That much was known. The part that changed in 2026 is that the LIGO-Virgo-Cagra collaboration released their biggest catalog ever. NUM 390 confirmed detections of black hole mergers, 161 of them new, from a single 10-month observing run, 3 to 4 collisions per week. Not per year, per week. And inside that catalog, buried among the routine mergers, were events that did not fit. Some of the colliding black holes were too heavy, heavier than a dying star should be able to produce. Stellar physics puts a ceiling on how massive a black hole can be when it forms from a collapsing core, roughly 50 to 60 solar masses, depending on metallicity and mass lost during the star's life. Several of the mergers in the new catalog involved black holes above that ceiling, which means they did not come from a single star. They came from a previous merger. They are second-generation black holes, objects that formed by collision and then went out and collided again. That is a genuinely different kind of object. It is not the corpse of a star. It is the product of a collision between corpses, and it raises a question that is still open. How many generations deep can this go? If a second-generation black hole merges with another second-generation one, you get a third-generation object, one that is the accumulated product of 4 or more original stellar deaths. And if those merge, the implication is that the supermassive black holes at the centers of galaxies, the ones weighing millions or billions of solar masses, might have been built this way, not from a single collapse, but from a chain of mergers stretching back billions of years, brick by brick, collision by collision, a slow, violent assembly line running since the early universe. And that assembly line is still running, right now. 3 to 4 times a week, somewhere in the observable universe, 2 black holes spiral together, merge, and produce something heavier. The universe is building black holes out of black holes. And it has been doing it for a very long time. Which brings us back to wind. But not the distant galaxy-spanning winds from Act 1. This one is closer to home. Our own galaxy, the Milky Way, has a supermassive black hole at its center, Sagittarius A star, about 4 million times the mass of the Sun, 26,000 light-years away. And for half a century, it had a problem. Every other supermassive black hole we could study was producing a wind. Jets, outflows, energy pushing outward. That is what the physics says should happen. When matter falls toward a black hole, some of it must be pushed back out. Sagittarius A star appeared to produce nothing. No wind, no jets, no outflow. Just silence, which would have made it the only exception in the known universe. 50 years, that question sat there. Why is our black hole the quiet one? In June 2026, astrophysicists at Northwestern University, Mark Gorski and Lena Murchikova, published the answer in the Astrophysical journal Letters. They combined 2 instruments. ALMA, an array of radio telescopes in Chile, which maps cold molecular gas, and Chandra, NASA's X-ray observatory in orbit which sees hot gas. And what they found was not the wind itself. It was the hole the wind had made. A cone-shaped cavity near the galactic center, swept almost completely clean of cold gas, with the tip of the cone pointing directly at Sagittarius A star. Something had cleared that region out, and the energy required to do it could only have come from one place. The wind was there the whole time. It has been blowing for at least 20,000 years. So why did it take half a century to find? 2 reasons. First, the center of our galaxy is buried behind enormous quantities of gas and dust. Only recently have instruments become sensitive enough to see through it clearly. Second, and this is the more interesting one, Sagittarius A star is currently in a quiet phase. It is not feeding aggressively. Its wind is not the hurricane that other black holes produce. It is closer to a breeze. It was never missing. We just could not look properly. And that, honestly, is a theme you will see in almost every act of this video. The black hole was doing exactly what the physics predicted. We just did not have the instruments, or the patience, or the right angle to see it. Now, everything I have told you so far is confirmed, peer-reviewed, published, verified. This next one is not. And I need to be honest about that up front, because the claim is extraordinary, and extraordinary claims require extraordinary evidence. On November 12, 2025, both LIGO detectors and Virgo picked up an exceptionally faint gravitational wave signal. The designation is S25112 centimeter, and the chirp mass, a specific combination of the two merging objects' masses, came in between num 0.1 and 0.87 solar masses. There is a greater than 99% probability that at least one of the objects was lighter than the Sun. That should be impossible. Here is why. When a star dies, the remnant it leaves behind depends on its mass. Below about 1.4 solar masses, the Chandrasekhar limit, the dead core becomes a white dwarf. Between 1.4 and roughly 3 solar masses, it becomes a neutron star. Only above about 3 solar masses can a dead stellar core collapse into a black hole. No dying star can produce a black hole lighter than the Sun. The physics does not allow it. And white dwarfs are not compact enough to produce a gravitational wave signal that LIGO could detect. And the probability that this system contains a neutron star is less than NUM 8%. So if it is not a white dwarf merger, and it is almost certainly not a neutron star, and it cannot be a stellar black hole, what is it? The leading explanation, if the signal is real, is that at least one of these objects is a primordial black hole, formed not from a dying star but from density fluctuations in the earliest moments of the universe, before any star had ever existed. Primordial black holes have been theorized for decades. They are one of the leading candidates for dark matter, the invisible substance that makes up roughly 27% of the universe's total mass energy. If confirmed, this would be the first direct detection of a primordial black hole, and it would extend our ability to study the universe all the way back to the moments after the Big Bang. But, and this is the honest part, the signal has a preliminary false alarm rate of roughly 1 per 6 years. That means it is statistically rare, but not impossible, as detector noise. It is not in any formal catalogue. It may not survive further analysis. It might be nothing. And it might be nothing is the correct scientific position. That is not disappointing. That is the process working. If it is real, we will know. More data will come. More signals will appear. And the catalogue will do what catalogues do: separate the real from the noise. But if it is real, if even one primordial black hole has been found, then the universe just became a fundamentally different place than we thought it was yesterday. Speaking of things we thought we understood, there is a prediction that sat untested for over 50 years, made by a man who died before it could be proven. In 1971, Stephen Hawking proposed something called the area theorem. It says that the surface area of a black hole's event horizon can never decrease. It can stay the same. It can grow, but it can never shrink. For 55 years, nobody could test it, because testing it requires measuring the surface area of something you literally cannot see, before and after a merger, and comparing the two. You need to know the size of both black holes before they collide. Then you need to know the size of the one they produce. And you need the measurement to be precise enough to tell the difference. The LIGO catalog, the same one that contains 390 mergers, finally had a signal clean enough to do it. It was the clearest gravitational wave ever recorded. Signal-to-noise ratio of NUM 76.9. The waveform was sharp enough to extract the horizon areas before and after with real confidence. They measured it. The horizon grew. Every time, confirmed to NUM 99.9999% confidence. Hawking was right. He predicted it in 1971. He died in 2018. The proof arrived in 2026. He never saw it. But the theorem holds. And it holds not because someone proved it in a theoretical derivation. it holds because the universe was measured doing exactly what he said it would. Out. There is something worth sitting with in that. A man in a wheelchair, unable to move or speak without assistance, wrote down an equation about the surface area of an object no one had ever seen. And 55 years later, an instrument that measures distortions smaller than the width of an atomic nucleus confirmed he was right. That is what physics is, not guessing, not hoping. Writing down what the universe must do, and then waiting, as long as it takes, for the universe to agree or disagree. Now, I said at the beginning that this video would change how you think about everything above your head. And this is the act where that stops being a metaphor, because the galaxy you are sitting in right now, the Milky Way, flipped on its side. Not metaphorically. The entire disk, every star, every spiral arm, the whole flat plate of light you see when you look up on a clear night. It tipped over by more than 90 degrees. About 10 billion years ago, the Milky Way was hit head-on by another galaxy. A dwarf galaxy astronomers call the Gaia sausage, named for the shape its stars make on a velocity plot. And the collision did not destroy us. It torqued us. Here is how they worked it out. In July 2026, an astronomer at Durham University named Kirill Batrakov presented results at the Royal Astronomical Society meeting. His team simulated NUM 25 galaxies like ours, from the early universe to the present day. A pattern appeared. Almost every galaxy with a slowly rotating outer halo had done two things: survived a major head-on collision and flipped. The Milky Way has a slowly rotating halo, and we already know about the head-on collision. Then a completely separate team, led by Ling Zhu, used the motions of more than 600,000 giant stars to reconstruct the shape of our dark matter halo, the invisible scaffolding that holds the galaxy together. They found the outer halo sitting almost perpendicular to the disk. Two teams, two completely different methods, same answer. The disk we live in got turned, while the outer halo kept its original orientation, like a wheel that was rotated while its shadow stayed where it was. Nobody watched this happen. No telescope can film something that unfolded across billions of years. This is reconstruction, forensics, not photography. But when two independent lines of evidence point the same direction, that is usually how astronomy arrives at the truth. The constellations our earliest ancestors looked up at are not the ones we see. The sky is not fixed. It just moves slower than we do. So let me pull all of this together. Because if you have stayed this far, and genuinely thank you if you have, then you have now seen 8 separate ways that black holes broke what we thought we knew. Their winds reach further than galaxies. They wander invisibly through space. They build themselves from each other. Our own black hole was hiding its wind for 50 years. One might be too small to have come from a star. Hawking's theorem survived half a century of silence, and the galaxy we live in was turned on its side by one of their collisions. Slow. The picture that emerges is not the one most people carry in their heads. Most people think of a black hole as a drain, a point of no return, an object that sits there and swallows things. Passive, final, dead. That is not what the data shows. What the data shows is that black holes are engines. They regulate whether stars form across hundreds of thousands of light years. They merge and grow across billions of years. They shape the structure of galaxies, including the one you are sitting in right now. They are not endpoints. They are infrastructure. The universe uses them. It uses them to control the temperature of galaxy clusters. It uses them to redistribute angular momentum. It uses them to build larger structures from smaller ones. It uses them to do things we are only now, in 2026, beginning to measure. And here is the part that keeps me up at night. We have been studying black holes seriously for about 60 years. In that time, we have gone from they might not even exist to they regulate the formation of stars across the observable universe. Every decade, the picture gets bigger, more powerful, more connected. Every time we build a better instrument, LIGO, James Webb, ALMA, Chandra, the black holes turn out to be doing more than we thought, not less, more. Which raises a question that no one can answer yet, but that I think is worth asking out loud. If black holes are already doing this much, shaping galaxies, controlling gas, building themselves across cosmic time, what are they doing that we have not even thought to look for yet? What is the next instrument going to show us? What are we going to find in the next catalog? And when we do find it, will it be something we predicted? Or will it be something that, once again, breaks what we thought we understood? If you made it here, seriously, thank you. This was a long one, and I do not take that time for granted. If any of these 8 discoveries changed the way you think about black holes, or about the universe, or honestly about anything at all, drop a comment and tell me which one. I read every single one. And if you want more of this, facts that are verified, sourced, and honest about what we know and what we do not, subscribe to MindSnap. I post every week, and I promise you, the next one will be just as unsettling as this one. Follow MindSnap. Facts that change how you see everything.